Section: Introduction. In this section, we discuss how long context language models, LCLMs, have the potential to revolutionize artificial intelligence by simplifying tasks and applications without the need for complex tools and pipelines due to context limitations. By combining various processes into one model, LCLMs improve efficiency and reduce errors, offering a more straightforward approach to model development. Techniques like adding instructions, using few-shot examples, and chain-of-thought prompting can be seamlessly integrated to enhance LCLMs for specific tasks. However, fully realizing the capabilities of LCLMs requires thorough evaluation on genuinely long context tasks relevant to real-world applications. Existing benchmarks fall short as they often rely on artificial tasks or fixed-length datasets that do not keep up with the evolving definition of long context. These evaluations do not sufficiently challenge LCLMs on groundbreaking tasks. To address this gap, we introduce the Long Context Frontiers (LOFT) benchmark, which includes 6 tasks with 35 datasets covering text, visual, and audio data to push LCLMs to their limits and assess their real-world impact. LOFT differs from previous benchmarks by allowing for the automatic generation of longer context lengths. While the current version extends to 1 million tokens, it can be easily expanded to tens of millions for comprehensive evaluation as LCLMs advance. LOFT focuses on areas where LCLMs can bring significant changes, such as retrieval, augmented generation, RAG, SQL processing, and many-shot in context learning, ICL. The LOFT benchmark introduces a new research direction on long context prompting, specifically corpus in context, CIC, prompting. We evaluate various LCLMs on LOFT tasks and compare their performance with specialized models optimized for each task. Our evaluation shows that LCLMs can perform comparably to specialized models on many tasks but have room for improvement in complex reasoning tasks. Different prompting strategies impact performance, highlighting the need for further research to enhance the robustness and effectiveness of LCLMs. Overall, our results on LOFT demonstrate that LCLMs can compete with specialized models while also indicating areas for improvement in long context reasoning as context sizes increase. Section Summary. In this section, we introduce Long Context Frontiers, LOFT, a benchmark comprising 6 tasks with 35 datasets that span text, visual, and audio modalities to rigorously evaluate long context language models, LCLMs. LOFT challenges LCLMs by automatically increasing context lengths up to 1 million tokens, pushing them to their limits in tasks like retrieval, augmented generation, RAG, SQL processing, and many-shot in context learning, ICL, highlighting areas where LCLMs excel and areas needing improvement. Our evaluation on LOFT shows that while LCLMs can match specialized models in performance, there is still significant room for enhancing their robustness and reasoning abilities as context windows scale. Section: Retrieval and RAG. In this section, we include various text retrieval and RAG datasets that cover a range of retrieval tasks such as BEIR, multi-turn conversational QA, multi-hop QA, and multi-target QA involving set operations like unions or differences. We also incorporate multimodal datasets that include images, videos, and audio for retrieval tasks. All queries in each dataset share a common corpus to mimic real retrieval scenarios. To create this shared corpus, we gather all gold passages from a few shot, development, and test queries, and then uniformly sample passages until we reach the desired context size. This method ensures that smaller corpora, for example, 128K, are subsets of larger ones, for example, 1M. We shuffle gold and random passages to prevent positional biases. For fair evaluation, specialized retriever models also use the same corpora. We also adapt datasets from Big Bench Hard, BBH, and Long ICL Bench, LIB, to assess many-shot in context learning, ICL, capabilities. Similar to retrieval, we construct shared many-shot ICL contexts to ensure that training examples in smaller contexts are included in larger ones. Since all many-shot ICL datasets are classification tasks, we make sure that each class is represented at least once. For evaluating SQL-like reasoning, we use Spider, a single-turn text-to-SQL dataset, and Spark, its multi-turn variant. Each query's corpus consists of an associated database with one or more tables. To construct the corpus for each context length, we select databases where all tables fit within that context length. This means that the largest databases for the 1M token setting would not fit into smaller context lengths. Therefore, unlike other tasks sharing a corpus, the query sets vary across different context sizes. We create a corpus up to 0.9 times the maximum context length to accommodate differences in tokenizers and leave room for instructions and formatting. We introduce corpus in context prompting, which allows large corpora to be directly processed within the context window of LCLMs. This approach combines established prompting strategies tailored to leverage LCLMs' capabilities for learning, retrieving, and reasoning over in-context corpora. We provide task-specific instructions to guide the LCLM's behavior and insert the entire corpus into the prompt, assigning a unique identifier to each candidate in the corpus. Few-shot examples are given to help the LCLM understand the desired response format and improve task accuracy. The queries are formatted similarly to few-shot examples, and for multi-turn datasets, previous query turns and model outputs are prepended to the current query turn to condition the model's generation on its prior responses. Section Summary. In this section, we include diverse text retrieval and RAG datasets that cover various retrieval tasks, including BEIR, conversational QA, multi-hop QA, and multi-target QA. We ensure that all queries in each dataset share a single corpus to mimic real retrieval applications, with gold and random passages shuffled to avoid biases. Additionally, we adapt datasets for many-shot and context learning, ICL, and evaluate SQL-like reasoning on Spider and Spark datasets, ensuring that each class is represented at least once and constructing shared contexts for training examples. Section: Design Consideration. In this section, we consider the design aspects of CIC prompting techniques. We acknowledge that the context lengths can vary significantly due to differences in instructions, formats, and tokenizers. To address this diversity, we emphasize the importance of allowing sufficient space for prompt customization, as explained in the dataset section. It is crucial for fair comparisons among LCLMs that each model, such as LOFT with a maximum context length of 32K or 128K, only utilizes the corpus and examples available in that specific version without truncation. When it comes to efficiency, encoding a context with 1 million tokens can be time-consuming and computationally intensive. One advantage of CIC prompting is its compatibility with prefix caching in autoregressive language models, where the query is placed at the end of the prompt. This approach enables encoding the corpus just once, similar to traditional information retrieval indexing, without compromising the performance of LCLMs. We then move on to discuss the LOFT tasks and primary results. We evaluate three top LCLMs: Google's Gemini 1.5 Pro, OpenAI's GPT-4o, and Anthropic's Claude 3 Opus, on LOFT. These models were chosen because their APIs support various modalities, with maximum context lengths of 2M, 128K, and 200K tokens, respectively. The evaluation is based on their official APIs, and prompts are selected based on their performance on development queries within the 128K token context. In cases where a small number of API calls are blocked, they are considered incorrect. LCLMs without task-specific fine-tuning are compared against specialized models that have undergone extensive fine-tuning for specific tasks. For text retrieval, we utilize Gecko, a leading dual-encoder model fine-tuned for text retrieval and similarity tasks. To ensure a fair comparison, both LCLMs and Gecko are tested on the same corpus instead of using separate retrieval corpora or published results. The results show that Gemini 1.5 Pro performs similarly to Gecko at a 128K context length, with other LCLMs also demonstrating strong performance. Despite not undergoing specialized contrastive learning for retrieval, LCLMs show potential for retrieval tasks. Further analysis on the positioning of documents in longer contexts reveals insights into performance variations, indicating the model's ability to focus on specific document locations for improved recall. In visual retrieval tasks, we employ CLIP L14 as the specialized model and evaluate performance across different benchmarks. Gemini 1.5 Pro outperforms GPT-4o and maintains an advantage over CLIP across all visual benchmarks and context lengths. Section Summary. In this section, we address the design considerations for CIC prompting techniques, emphasizing the importance of accommodating diverse context lengths through prompt customization and fair comparison guidelines for LCLMs. We also discuss the efficiency benefits of CIC prompting, highlighting its compatibility with prefix caching in autoregressive language models and its ability to maintain performance without additional encoding steps. Additionally, we evaluate state-of-the-art LCLMs on LOFT tasks, showcasing their performance against specialized models and the potential of LCLMs for retrieval tasks, especially at 128K context length. Section: Audio Retrieval. In this section, we selected PaLM 2D as our specialized model, which aims to make audio and their transcriptions similar. It has previously shown top performance on the FLIR datasets. Currently, GPT-4o and Claude 3 Opus do not handle audio input. Gemini 1.5 Pro performs similarly to PaLM 2D across 5 languages. Notably, Gemini 1.5 Pro excels over PaLM 2D in Hindi, likely due to differences in their pre-training data. Our results confirm Gemini 1.5 Pro's strong performance across various context lengths, showcasing the capabilities of LCLMs and the need for more challenging audio datasets. We established a retrieve and read RAG pipeline using Gecko to retrieve the TOP40 documents. These documents are then used in conjunction with Gemini 1.5 Pro to generate answers based on questions and retrieved documents. Gemini 1.5 Pro outperforms the RAG pipeline on multi-hop datasets like Hotpot QA and Musique, as it can reason over multiple passages in the context window using chain of thought. This is a capability that RAG pipelines typically lack unless they have a separate module for planning and reasoning. Gecko, a specialized retriever, excels at ranking relevant passages, making it beneficial for multi-target datasets like Quest and QAMPARI. To further explore LCLM's abilities, we conducted closed-book ablations on Gemini 1.5 Pro, removing the corpus from the context to evaluate its performance based solely on parametric knowledge. The results show that closed-book performance lags behind long context and specialized models, emphasizing the importance of leveraging external corpus for enhanced reasoning capabilities. We also examined SQL-like compositional reasoning, where LCLMs show reasonable performance but still fall behind specialized pipelines, indicating room for improvement in their reasoning capabilities. Analyzing the reasoning capabilities of Gemini 1.5 Pro, we found that averaging is the most challenging operation, while counting is relatively easier. Reasoning over equality is notably easier than reasoning over inequality. In many short ICL tasks, Gemini 1.5 Pro outperforms GPT-4o on most benchmarks, except for BBH Tracking 7. Claude 3 Opus achieves the best average performance among LCLMs on this task. Scaling many short ICL tasks shows that increasing the number of examples improves accuracy in some tasks like libdialog, but not in reasoning-intensive tasks like BBH Tracking 7 and BBH Web, suggesting a limit to how much models can benefit from scaling with more examples in complex tasks. Section Summary. In this section, we focus on audio retrieval using the PaLM 2D model, which excels in maximizing audio transcription similarity and has shown state-of-the-art performance on FLIR datasets. We observe that Gemini 1.5 Pro performs comparably to PaLM 2D across multiple languages, with a notable advantage in Hindi likely due to differences in pre-training data. Additionally, we explore the use of a retrieve and read RAG pipeline with Gecko for document retrieval, showcasing Gemini 1.5 Pro's superior performance over RAG on multi-hop datasets like Hotpot QA and Musique, highlighting the model's ability to reason over multiple passages effectively. Section: CIC Prompt Ablations. In this section, we perform experiments by changing different aspects of the CIC prompt. We look at how these changes affect the performance of Gemini 1.5 Pro on the 128K version of LOFT. The results of these experiments demonstrate the effectiveness of our CIC prompting design. When we remove task-specific instructions or chain-of-thought reasoning, the model's performance worsens. Similarly, using a separate corpus for each few-shot example instead of a shared corpus also leads to a decrease in performance. This could be because the few-shot examples help the model focus on the test corpus or because the few-shot task becomes too easy compared to the evaluation task. Placing the query at the beginning of the prompt instead of at the end results in a significant drop in performance across different tasks and models. This indicates that caching the prefix works better than encoding the corpus based on each query, which would be more computationally expensive. Changing the way document IDs are presented, such as using random alphanumeric IDs instead of numerical IDs, negatively impacts performance in most datasets. Additionally, only placing the IDs at the front of the document instead of at both ends also leads to a performance decrease, showing that repeating text can help compensate for missing context in language models. To understand if the model relies on context or parametric knowledge, we remove the document content and only keep the title and ID in the corpus. This significantly reduces performance, suggesting that the model indeed depends on the provided context. We also investigate how the number of few-shot examples in the prompt affects quality and find that increasing the number improves performance on the retrieval task. Furthermore, we discuss the challenges in evaluating LCLMs due to limitations in existing benchmarks. While some benchmarks focus on synthetic tasks like needle in a haystack retrieval, they may not fully capture real-world retrieval or reasoning tasks. Our work extends the evaluation of LCLMs to longer contexts and diverse tasks, providing insights into how these models perform in more realistic scenarios.